here. They get some stuff and he's also a genius. He didn't bring a bag or something. Basically, he watched it. So I can't do I don't. He just gets to complain about being bored all day. And he could have prevented you about 4,000 different ways.
I don't forget my lines because it was in my bag. That night. So I guess
So we had a fantastic first day of the symposium. We'll have a great second day of the symposium as well, I'm sure. And so our first speaker is Joshua Maldonado from OU. And he'll talk about a greedy emulator for nuclear two-body scattering. Go ahead.
Hello, I'm Josh. And just like was mentioned, I'm talking to you about a greedy emulator for nuclear two-body scattering. This is work that I've done with Drischler and Dick Fernstall. First, what am I going to talk to you about today? I'll give you a brief motivation behind this. I'm sure all of you know the motivations behind a lot of nuclear physics and emulators, but I'll give you a little bit. I'll talk to you a little bit about the emulator itself, and then about my numerous implementation for getting high fidelity solutions. After that, I'll talk about error estimates and my greedy approach. And lastly, the next step I'd like to take. Okay, so first, some quick motivation. There are many things to motivate this. Two big ones are mining scattering data. Obviously, we want to get real data to motivate our models for testing and validating and improving them, as well as the motivation of uncertainty quantification and parameter estimation. I think this plot here took 20 million evaluations to get. So obviously, if those evaluations, all those solutions took a long time to get, a long time times 20 million is no good. So if you have a faster, better way of getting those, that can be used.
What are we looking on the left, cross sections of different energy?
I think so, although I don't fully remember.
It's a fixed energy for him, neutrons on calcium, and it's just differential restriction as you change the angle. The reason why you have three is because you're changing the parameters of the interaction.
There's two curves on each one, so it's just showing the emulator and the high fidelity. Okay.
And quick shout out to those all the figures. Yeah, thank you.
And one more, sorry for interrupting. And of course, you have imaginary quantities, imaginary potentials, right? Optical potential.
Yeah, I believe this is the optical potential most. So next up is emulators. I'm sure you've all seen this figure I'm going to show you fully in a minute here, but I'll show it to you again. So first of all, an emulator, if you're going to emulate something, you better have something to emulate. This is an example, we'll have the example of an eigenvalue problem called bound state. I'll mention this again in a second, but notably, I am not looking at a bound state calculation. I'm looking at a parametric differential equation. More on that in a second, but the kind of mechanic behind it is the same. You have some form of high fidelity system. And what you can do with that is you can solve it a couple times to get a snapshot basis of exact solutions. And with those, you can project them onto your onto that same high fidelity system, and you're left with a small matrix or perhaps a tiny pile of small matrices. And doing that will conclude the offline or training part of your emulator. Once that is done, you can actually go ahead and use it in the online stage. And with those much smaller matrices, actually use them to get the quantities that you want. Like I just said a second ago, I am notably not looking at a bound state calculation. I am solving this parameterized differential equation. So my energy is fixed and it's positive. That will slightly change the online phase, and I'll talk about that more in a second. But here, my high fidelity system, instead of just being that one matrix, will be these pieces in orange. And then the thing that I'm actually trying to emulate here is the scattered wave unit. And notably the scattered wave plus the free solution here, you'll just get your full wave back, which is that same wave mentioned. So I mentioned it's going to change the online stage a little bit. So here I'll throw a pile of equations at you. So kind of the main thing I'm after is this coefficient vector beta, that when I have that, I can actually put that onto my snapshots and get my emulated wave. To get that, I'm going to need this big omega and little omega quantity, which I get with these equations. So to kind of walk through that a little bit, this, again, orange block is going to be my high fidelity pieces that you see in both the process for getting the big and little omega. The snapshots that you see are exactly those. And here, the notation here is intentional, A, X, and B, which you'll see again in a second. And notably here, kind of the power behind this and being able to build this emulator is that this theta here, which is inside of your high fidelity pieces, has, I guess in my case, has an affine decomposition, which you can motivate that little piece. And because of that, you can actually pull it out, and you're left with exactly this pictorial piece, which are analogous to these calculations. There we go. So something I did not mention is how exactly to get this snapshot basis. This was mentioned briefly in a question during a talk yesterday. You might mention Kyle's lovely talk, talking about some really cool stuff. During this talk, he was quickly mentioning, I'm building a snapshot basis for my emulator. Patrick was sitting up in the front row and asked a quick question. I don't know if everyone caught it, of wait, how exactly are you choosing your snapshot basis? Because this is an important question. Not all snapshot bases are created equal. He said, well, I have some high fidelity solutions. I'm taking a PUD of them and calling it good. And then he kept on telling us about some really neat stuff.
I'm sorry, how long did you spend dropping these out?
The iPhone, you can just copy subjects, so only a couple seconds.
That's how old I am, I don't know how to use an iPhone.
So to maybe talk about that a little bit more in detail, for my differential equation, I need some kind of parameter space. So here I have the Minnesota potential, which is the potential I'll use for the duration of this talk. It has these two pieces, these two Gaussians. I am keeping the two kappas fixed, which means I'm only varying the R and the S. And you see exactly on the plot on the left, the R and the S. Because of that, this does have an affine decomposition. But now I have this parameter space here, and like Patrick's wonderful question, how exactly should I build my snapshot basis? I have all of these candidate locations, which ones are the right ones or even a good one? And like Tyler will be answer that question. A standard approach is to kind of sample the space in a space filling way with high fidelity solutions, and then take a POD and take the good ones from that. And that is certainly a good way to do it.
So can I interrupt again?
Yes.
So what is the Minnesota potential? Is that something fed with two-body data and Lutherons, or what is it?
Forget specifics. I think it's just a super simple potential that is for two body.
Two nuclear,
I'm sorry?
two nuclear.
Yes.
Okay.
Yeah, there's no equivalent force here.
Do you recall why it's two terms? Because if you just want to say the scattering length in one channel, then, or even the effective range and scattering length in one channel, then one Gaussian would be enough. Do you recall why it's the sum of two?
No, but I can tell you the source that I got this from. This was from a lovely paper by Dick Fernstall. He used, I think, a two channel Minnesota potential, and I just ripped one of them.
Just look at the shape of these things, there's a repulsive short range and attractive.
They thought they
It's
still-
just a toy potential, a toy model of that the folks in Minnesota, and it's just a convenient one to test things.
It does some pretty simple and quick calculations to make sure any machine is up and running pretty well. Okay. So before I can talk about where it is a good, before I can say where to put the good high fidelity solutions, I might want to talk about how I actually get those high fidelity solutions. And for that, I use Numero. The Numero OD is up in the corner. But notably, it just doesn't have a lifetime term. And I think this is a relatively not uncommon choice. Specifically, I use this cast into a matrix equation, as you see by the giant matrix equation in front of you. And here, I cast it into a matrix equation for a couple of reasons. One is because it's highly sparse and lower triangular, with a pretty low bandwidth. Also, by solving for these scattered waves, I can also solve it with the initial conditions of 0 for the wave and its derivative. So that's just driven by its inhomogeneous term, at least at its first point. And notably here, Numerov scales with error to the 6th, or its error scale with step set to the 6th. But this first row here, which you see is a little bit different than the rest, can kind of dictate how well Numerov does throughout your calculation. And I will show you that now.
So can I continue? So if you don't want me to interrupt, just.
No, go for it.
So the differential equation you need to solve for a scattering problem is homogeneous, right? So where is the inhomogeneous term appearing?
Here. So there is a homogeneous version of this equation. This is just the inhomogeneous where you only solve for the scattered wave. I don't know if that answers the
For
question.
scattering, it's always inhomogeneous. For scattering, it should always be inhomogeneous.
No, I mean, if that equation is equal to 0, right? And then you look at the behavior at large distances, you extract the spaceship.
Yes.
So that's the full, you know, if you wrote the equation for psi, that's what you used to do. It sounds like,
Yeah, and
but split it up into the 3D solution, which is forcing a normal.
Okay, I agree. Thank you.
This first one I mentioned is slightly different. This is, I forgot to point out, thanks to some work by Gonzalez and Thompson back in the 90s. Here, so to see exactly how that first row affects your answer throughout, how it affects the wave function, I have the same wave function solved in three different ways. I took one to be solved with R carries 5, which is an adaptive method. I shot down the tolerances and call it exact, as you do. The purple line that you see sitting on top of it is exactly what you see in this previous slide with this start. And then the green line on the next slide is this replaced with just a simple FOIL step. And you can see exactly how much that first term will dominate the area throughout the space, because these differ by a good, 4 orders of magnitude. Yeah. Okay, so I forgot what my next slide is. Okay, good. So another key point of casting this into a matrix equation is that the error estimator that I use is good for any matrix equation AX and B. How I actually estimate these errors is, I solve AX and B, and then I have the system AX and B, I should say, and I take out the X, which would be the exact solution, and I put in here my emulated wave, or my emulated solution, chi tilde, and then I take just the norm of it to get some kind of scalar quantity to try and judge how it's doing over the whole coordinate space in this case. This is approximately equal to the exact error, and you'll see, at least qualitatively, how approximate that is in the next few slides. And another really neat feature of this is that looking at its singular values will give you an upper and lower bound on how that error is doing. So to quickly point out, these two are the same. One just doesn't have the 2 norm around it. And kind of the takeaway from this is that the upper and lower bounds, well, there is an upper and lower bound bracket in your estimated error. So now I have all the kind of machinery that I need for my greedy approach, but I will real quick shout out some work done in a very similar area. This is work by Avik and Dean, looking at solving a parameterized differential equation using a BT method. And you will, if you haven't seen this figure, it's a neat paper. I think they go through 3 different models. And this is model 2, if you're interested. But you'll see very similar plots for me. So first, I should mention, what does greedy mean here? I've said it a couple times. Greedy here is making iterative decisions, and in this case, iterative decisions to try and minimize the errors across the parameter space. Here, so I guess I'll focus on the plot on the left first. I have, in this case, this is a one-dimensional parameter space example. So I'm keeping the R fixed and I'm varying the S. I have a couple things plotted. I have the purple line, the error estimate, and in practice, that's all I will have. But because of the choice of potential, I have access to everything all the time. So I'll show you that. You can see it is roughly proportional to the exact error in blue, and both of those errors are nicely tucked into the error bounds. Here I have 2 snapshots, one on either boundary of the parameter space, I will quickly point out that I am not suggesting that's the best choice. It is just an arbitrary choice to right here. And with those points down, or with those snapshots, I will scan the space and find its point of the highest estimated error, which is right here. So I will go through and I will keep adding snapshots until I hopefully achieve my tolerance goal of 10 to the minus 6 on the side. So like I just said, I scan the space, I'm gonna place a snapshot there, and then I do. So now I have 3 snapshots in my basis and 3 solutions to find them, or 3 high fidelity solutions for that. I will then scan the space again, find my new point of highest error, so highest estimated error. And I'll keep doing the same scanning and placing iteratively until I have, in this case, met my tolerance goal of 10 to the minus 6 across the space, which is just an arbitrary choice for an example. So there we go. At this point, I say, okay, great, I met my tolerance, I'm done. My offline stage is concluded. Now I notably ignored the plot on the right, so I'm gonna go back and talk about that for a second.
It's on the right side.
Yeah. So all of these decisions were made based on the wave function. And the resulting phase shift from those scattered waves are shown. You see the exact in the solid line and the emulated in the dashed. Here, the 2 snapshots are again on the boundary because I rewound. And on the boundaries, or on those snapshots, I should say, it's fixed to the exact phase shift. I had the 3rd, it's now fixed there. It's doing a little bit better across the space. At the 4th, looking better. And the 5th, at least on this scale, it looks like it's overlapping. And there we go. So to look at exactly what's happening at the for the phase shift or for the scattered waves here, I have a quick, how is this doing? In green, I have those snapshots. They are orthonormal to each other. I just scale them up for your viewing pleasure. In the exact solution here is in gray, and the emulated solution is in the purple dash. And you can see exactly how well it's doing, at least in the difference in that level plot.
Maybe we can save it for the end, but since I just occurred to me, maybe I can ask now. So have you investigated how much does this greedy technique do, like on average, outperform just the space filling for the same number of snapshots? Is there any results from that?
Not yet. That's something I'm looking into shortly. I saw Patrick Henry.
So on the previous slide, so you're choosing where to put your next point based on the estimated error in the wave function. What if I don't care about the wave? What if I actually only care about the phase shift? Can you do this error estimation and picking the next point based on some observable estimated error alone?
That is exactly one of my bullet points in my next steps. So there you go. I saw Kyle's hand next.
Yeah, it's just a response to you, Sebastian. Whenever we did the growth of the SD problem, I think we got about 2 orders of magnitude better for greedy versus
That's pretty cool.
something like that.
I think in general, it's gonna depend on the problem.
Yeah.
Yeah, it does. I was just like wondering here because I mean maybe this is like 1D and it might be more difficult here, but I can easily see how in higher dimensions it should have.
Actually, that comment very similar to, it's about the phase shift. And I'm thinking that when you estimate the phase shift, actually you care about the wave function at the matching point.
Yes.
So instead of doing the norm of the whole matrix difference, you can probably focus just in places of, in the region of X, which is close to the matching point. And that is probably going to be much more correlated to the phase shift than the whole wave function.
I believe it. But yeah, I do find the phase shift by matching out at a far distance.
Right.
Yeah.
But when you put the difference in the wave function into a matrix norm across all X.
Yes, yeah.
But if instead you would focus only around the matching point, that is probably going to be more correlated to the phase shift itself. Like the error that you're making the wave function in that area with large R is probably going to be very, very correlated to the error that you're making in the phase shift. In a sense, you don't care. You're reducing the wave function of short distance.
That's a good point. Thank you.
I'm not so sure because what happens at short distances, you integrate there and the differential equations actually relates that phase shift to those changes. So it's like, I wouldn't be so sure because they're related.
Yeah, sure. But in pretty, you can find the linear combinations that, that doesn't look great, but no.
For the emulator.
Yeah, just for the emulator.
Yeah, for the emulator.
In general, I agree with you, but
Okay.
just for the emulator.
Yeah, that's a good, okay.
Yeah,
so you said like you extract phase shift from the asymptotic behaviors. But there's a second way, as Sebastian mentioned, right? You can do overlaps, like which put emphasis on the internal wave function. overlap with the weight function with some other vectors, and that vector has a weight on the internal weight functions.
Okay,
Like means function method. Because you have weight functions, so.
I have not tried that, and that sounds interesting to try. Alright. Good. So, yeah, so I just showed this, related to one of the questions, this was a one-dimensional parameter space, that might beg the question, how did this do in more than more than one dimension parameter space? So here I have a two-dimensional parameter space. This is the exact same space that I showed you before with all the Minnesota potentials and all the green candidate snapshot locations. Here I have placed 4 snapshots, one on either corner. I will again give the disclaimer that this is an arbitrary choice, and by no means am I trying to say it's the best choice. It's just for the sake of example. I have the estimated error shown in the color bar and in the blobs of color. And notably, this color transition will happen at that mean value of the estimated error. And these thinner contour lines are the exact error, and you can see their rough proportionality to the estimated error as well. So here I have 4 snapshots. I've again scanned the space. That big old red X is going to be where my highest estimated error is. So I'm going to place a new snapshot there. And I'm going to again do the same iterative scanning, placing. In this case, I don't have a specific tolerance threshold that I'm looking at. I just told it, give me 10 snapshots. Let's see how it does. So that's 9, and then 10. And throughout that process, you can see the estimated error drop down. So I asked my emulator to, or my algorithm to give me 10 snapshots, and then it did.
Josh?
Yes.
So in terms of color, I see that X and that yellow around, is that yellow around 10 or?
No, it's around somewhere around this color.
Oh, okay, thank you.
It probably would have been smart to add some kind of like maximum value because it does drop with the mean.
That's what I imagine was happening, so.
Yeah, good question.
Maybe you could change, like, differentiate the colors.
Yeah. So just like before, I built a basis and then showed you how it was doing with the wave function. I will again do that. But first, I will come back to the proposed question. If I have, in this case, if I have this parameter space, where should I place my snapshots for my emulator? If you listen to the last 10 or 15 or so minutes, you would say, or I would say, you should place them right there. Right? All of those green X's, and doing so will give you this result. These snapshots again in green, exact in gray, and emulated in the purple dash. And you see their errors here, well, their difference anyway, shown here. And this was my work. For some next steps that I would like to take, I would like to have some cohesive runtime and accuracy tests. Specifically, I'd like to compare the regular POD, some exact solutions approach compared to my greedy algorithm, which does use POD, but more in a author normalization method rather than a way to select my snapshots. I'd also like to look at a different potential, such as a local parallel potential. I mentioned before that all of these are with a Minnesota potential, which is nice and give me some quick computations. But I'd like to look at something more realistic. As well from that, I'd like to emulate some cross sections from that more realistic potential. I would also like to try and emulate some singular values from my high fidelity matrix. Because currently that is what takes the longest. And last, kind of on my little checklist over here for my next steps, is to try and look at some hyperreductions, look at non-affine problems, because currently all that I have shown you is restricted to an affine potential. And I don't want that restriction. Some challenges and or opportunities for collaboration. One, exactly as mentioned, I would like to propagate my errors to phase shifts and possibly cross sections, on maybe other observables as well. I would also like to see, how maybe where this greedy approach can be applied, because the only real requirement, at least for the error estimator, is solving the equation AX is B, which is obviously very general. And it also has the convenient structure of only having as many snapshots, or only having as many high fidelity solutions as your snapshot basis is large, which is convenient. I know potentially one area that has very high computation times for high fidelity solutions are with coupled cluster calculations. So maybe it's applicable there, maybe not. And lastly, I'd like to integrate this approach into some existing scouting emulators, such as rows, since it's lovely and open source. And that concludes my talk.
Josh, that was really nice, really nice. Other questions? Yeah, Pablo.
Fantastic talk, Josh. I really like it, and I love the cartoon character. I'm going to steal that in one of my future. You are.
You get paid, you get paid.
Very, very, very good. Two comments. The first one is to check. I think it could be useful to check something that's called one-shot learning. To make the connections with machine learning, and these type of ideas is if I have very few bullets to learn something that I get to learn, what are the approaches that could be used? I haven't checked that for myself, but it could be something useful too. And the second one, in terms of rows, I think this is a fantastic idea. More than happy to talk and see how we can merge the 3D step for selecting the basis. But I think most importantly is to use, because it's the same technology, to use it as an estimation for the error, to know when my emulator is starting to go astray. And for that, let me put on, can you go back to the first thing where you saw the Monte Carlo sampling for rows? A funny thing that happened is a day or 2 days before submitting the paper to the archive, I was running these calculations, and then I was like, I made a plot on the left based on points that were on the region where I trained. But if you see, the chains have moved to a different place where I trained. Is my error still within the bounds that I was expecting? And I run the same figure on the left, taking for the posterior, and you could see the difference between the emulator and the high fidelity solver. And if I had had some sort of siren or alert during my MCMC chain that is telling me, hey, your error is getting out of bounds, I would have stopped and say, okay, let me retrain the thing. So I think this will be fantastic if we were to incorporate it into some self-training thing for as you're going to the MCM system.
Yeah, Christian.
So I would like to follow up on this. So I agree with Pablo. But as you know, once you have the error estimator, the greedy part, you get almost for free. Both in terms of development time and runtime. So really the most computational demanding part is the error estimation, and especially if we want to estimate the singular values as well, either on the fly or in some sort of additional emulator that computes or emulates the singular values.
Okay, Sebastian.
Question for your output, you mentioned local chiral potentials. I presume that's because you want to keep using the simple differential equation to get the wave function, or what's the restriction there to local chiral?
That's a great question. Just because I heard it sounded good and I need a realistic potential to use. That said, it's not the only choice. And once I finish, I guess, tying up the Minnesota potential project and have it done, I'll take a closer look at what to use.
Yeah, I think the short answer is my personal bias, because I've already implemented this a long time ago. So it's in Ingo, so the GT plus potentials that we could just use on the fly. But I think Jane will be talking about this a little bit. I mean, this could be applied to the T matrix equation momentum space right away.
Yeah, it could be, but also my comment would be that also if you want to keep using wave functions, but you have a non-local potential in the Lippmann-Schwinger solver, you can always just take the half-chair solution Fourier transform, like integrate once to get this phi, and then keep using this machine equation.
Of course, yeah.
So just one question, how difficult will it be to include a long range Coulomb potential, for example? So you have people who have thought about that?
I have not thought about that. So,
Are there anticipated challenges or? Nothing new, nothing, yes, yeah, cool, right.
Okay, other questions for Josh? Yeah.
So in the field of algorithms, we use greedy to mean, take the best one immediately, don't do any kind of future search and all that. And almost always that means unoptimal. Now, that's not always, but it's very often true. What does a non-greedy version of this even look like? Is it even considered?
That's a good question.
Could you repeat the question, please?
So greedy, of course, just means take the best one immediately, but you can imagine, a scenario where after I chose that one, my choice for the next one is suboptimal just because I should have chosen like two unoptimal ones originally?
Oh, yeah, absolutely.
Non-greedy. So
Yeah.
what does a non-greedy version of this look like? Is it even conceivable?
Well, so in that definition, wouldn't be the POD just non-greedy?
No, I think what Patrick is saying is, if you go back to one of the slides where you had the error as you're pinning it down. Yeah, go one more. Okay, so in here you have two choices, where to shot those high fidelities is if I were to optimize those locations simultaneously. So I think, I think that will
Okay.
give you a different answer.
Yes.
I will bet that actually for this problem, they're not going to be that far. But I'm not, for the locations might be different, but the final estimate that final error bound that you get is not that much difference. But it will be very nice to see it, because in either way, you can say something about it.
But of course, it's all about trying to minimize the number of high fidelity coverage.
Yes.
So doing it non-greedily is probably just prohibited from the start. But I was just curious if it depends on it.
But the effective dimension for the solution manager is intrinsic. Right, as long as you find the basis, you're done.
All right, let's thank Joshua once again.
Right now, because it's a simple, in the future, no.
I think you can do that with action.
Okay.
We're good. Let me get this out of your way a little bit. Okay, our next speaker is Christian Drischler, also from OU, and he'll talk about a Bayesian mixture model approach to quantifying the empirical nuclear saturation point. Go ahead, Christian.
Yeah, so typically my talks are pretty long and so are my titles, so sorry about that, Dean. So I mean, as you mentioned yesterday, Dean, so this is impressive work that STREAMLINE has been doing. And I totally agree, but I also would like to thank you as the organizer of the symposium and of course the PI of STREAMLINE leading us through this project and so on. So thank you very much, and also to Elizabeth for organizing all of this. Okay, so today I'm going to be talking about nuclear saturation. I want to make the story pretty simple. I would like to address 4 questions, and the first one is, so what is nuclear saturation and how does it emerge? How well constrained is the nuclear saturation point, both from a microscopic picture and an empirical picture? How can we leverage empirical constraints from DFT, so density functional theory, to rigorously benchmark chiral effective field theory interactions? And this, of course, will have 2 pictures here in mind. One is a phenomenological picture from DFT, and the other one a microscopic picture from chiral effective field theory. And then finally, so what can we learn from all of this? What are the implications for the nuclear symmetry energy and its slope evaluated at the nuclear saturation density? So I'm going to give you my personal answers to those questions. If you would like to read more about all of this, we just archived this, I believe, on Tuesday, Tuesday. And also all the software package is available and distributed via the band framework. So you can do the same analysis, we do the same analysis by just cloning this GitHub repository. And I also would like to thank my collaborators on this, especially Zach Bezuli. So he was an undergrad student within the Summer Research Opportunities Program here at Michigan State University. And of course, Frederick Dean, who's the mastermind behind the statistical analysis or the statistical framework, all of this. And of course, Pablo and Hoffa, who are in the audience. So let's dive into this. So what is nuclear saturation and how does it emerge? So in the limit of infinite nuclear matter, so here's the energy per particle as a function of density at 0 temperature. Delta is the isosymmetry. So there are only 2 parameters, that the density and the isosymmetry symmetry, delta. So up here we have the equation of state in the limit of pure neutral matter. So very neutron rich, and then here down there is a symmetric nuclear matter. And as you can see, at the low density equation of state as a function of density, it's just characterized by a few low energy parameters, one of which being the nuclear saturation point down here. So in the limits of infinite nuclear matter at 0 temperature, the symmetric nuclear matter equation of state saturates. So it has a point where the pressure vanishes, where the derivative is 0. We call this point, or better to say the density, and not in the associated energy, ground state energy per particle, E naught, the nuclear saturation point. A point I use loosely in this talk, it may be a distribution function, but you get the idea. And so the question is, where exactly is that point? So the rule of thumb is the magic 16, 0.16 inverse Fermi cubed in density, and 16 MeV binding energy, roughly speaking. So, and from chiral effective heat theory point of view, which is the point of view I mostly adapt. So in neutron matter, all of the equations of state and many-body calculations are pretty well behaved. So here's the energy per neutron as a function of the densities of pure neutron matter. And typically at low densities, roundabout saturation density, perhaps slightly below, all of the calculations typically within the uncertainties agree pretty well. Unfortunately, there's no such plots in the region of symmetric nuclear matter. The uncertainties are pretty large. And so as you perhaps also can see here, so predicting the nuclear saturation point is typically a challenge for microscopic interactions. And so this makes nuclear, well, because there's a huge cancellation, a delicate cancellation between kinetic interaction, kinetic contribution, the Hamiltonian, and the interaction contribution in the Hamiltonian, which is particularly sensitive to three-body interaction. So here's, I think, a nice picture by Ruth Machleid and Francesca. So the energy per particle in symmetric nuclear matter as a function of density. I'm not so sure if I would trust chiral effective heat theory up to such high densities, but that's not the point here. So here they have just NN interaction, so no three-body interaction. If you add three-body interactions, the different topologies here, you end up with all the three-body forces here. And you can see, so typically the two-body interaction is too attractive, and then you need repulsive contributions from the three-body forces to nail this box here. That's the empirical saturation point. Where does this come from? Is part of my talk. So anyway, so there's a cancellation going on between the kinetic part and the interaction part, and especially that is especially sensitive to the three-body forces. So we can make predictions for this point here. So this minimum from various Hamiltonians, and here's a collection of those calculations, whole bunch of chiral interactions, two and then three-body interactions, all of which are delta less, except for the triangles here, delta full. And so this gray band is just to guide your eye. This is the so-called Köster anti-correlation band, if you like. So an important progress in chiral effective heat theory and the nuclear effective heat theory is that we no longer just have like point estimates for our observables, or I should say non-observables in this case, but also EFT truncation error estimates and more. So those two ellipses are bivariate normal distributions at the 2 sigma level with EFT truncation error. So contributions that we have not computed or cannot compute beyond N3LO in this particular case, fully quantified. And as you can see, even so, none of those interactions, delta less chiral interactions, actually saturates within that box, that empirical saturation point. And only this one here, which is the 450 MeV interaction, and the details don't matter, only barely overlaps with that box at the 2 sigma level. So typically what that means is that chiral EFT, given those calculations, is typically challenged by reproducing empirical properties of the nuclear saturation point. And yeah.
I'm confused, sorry for interrupting.
No, go ahead.
So what do you mean by empirical? You used this several times, and I would like to know, what do you mean by empirical?
Give me one slide, I'll show you. Yes.
It's actually a comment. So in reality, the symmetric nuclear matter equation of state doesn't really go to zero density because you have cluster everything. So if you go like, how much does that picture check? I mean, if now we're doing calculations which will show that it doesn't go to ab initio, which doesn't go to zero, but how does that change like say your estimate for the separation and
Um,
like the kernel will say.
that's a good point. So this is uniform matter. Perhaps we can discuss it after my talk. Would you mind?
No.
Perfect. It's an excellent point, but exactly. So the assumption is here uniform matter, which is
And
may not be a good assumption at low density,
the
right?
other question I have is, since now, I mean, some of the abilities we can reach left to away. Like if you were to show the density of the single Nucleon density of left to away from all of these interactions, would it be 0.08 for the protons and 0.08 for the neutrons, or no?
Well, so probably not. So is Gaussian in here?
No, yeah, you have to go.
Okay. Well, would be also something to discuss later, right? But so we only have one ab initio calculation of left to right, right?
Because there are some people that question whether the subversion point really is at 0.16 and minus 16.
I agree, which will be part of
Okay,
the next part. Yeah.
okay, thank you.
So, excellent question. So thank you very much. And of course, the saturation density is closely related to its typical interior density of a heavy nucleus. And I think we have seen this yesterday. The saturation energy is related to the volume term in the empirical mass formula. And so just to give you the number from inferred from P-Rex2, the interior density 0.148 plus or minus this inverse Fermi cube, slightly lower than this, but this is qualitatively consistent because again, we are here in symmetric nuclear matter, so delta is 0. And so led to as a finite isospin symmetry of 0.2, and the symmetry energy is positive, so the saturation point shifts a little bit in this direction. So corresponding the corresponding delta, the delta equation of state corresponding to the delta of led to A would be in between here. Okay, so it has a lower saturation point. So of course, one question is that perhaps something in the interactions or in the many-body frameworks? Is there something we are missing? Because most of those calculations are in fact perturbation theory. Perturbation theory is not guaranteed to converge, and that's why we've done the highest possible MBPT many-body perturbation theory calculations I know of through fifth order, and we okay, so we included residual 3N diagrams for the first time at third order. So I mean, the saturation is sensitive to three-body interactions. Perhaps maybe there was something to be seen there. And okay, there are a few things missing in here, especially the box here, which is unfortunate. But anyway, so you can see the convergence of MBPT, and it's typically pretty well converged for those soft interactions. But any of those diagrams cannot explain why the cluster band is shifted to the upper right. It still doesn't reproduce the empirical saturation point, and I'll get into the details of what that means in a second. Keep in mind that all of those interactions are constrained by the two and few body system only. So there's an extrapolation going on with additional uncertainties from the few body system all the way to infinite uniform matter. Yes.
You went, can you go back, sorry, keep going to the slide, but you skip over relatively quickly and say there's these few delta full calculations, but notably they fall into the box, and there are people who would say, even if you go to high order chiral potential, if you don't have the delta, then you might not have the breakdown scale that you want.
Yeah. So
are you reading anything into that? Because this is sort of striking that those
No.
delta full ones actually get into the box.
yes, I'll come back to this point, I'll promise. I'm not saying much about whether those points are inside the box because of two reasons. First of all, what are the uncertainties here? And second, where does this box come from? And is that should that be a uniform distribution? I don't think so. But in this case, it is. So anyway, so why is that?
There were some interactions which were also optimized to heavy nuclei. Okay.
Well, and to Osada, I think the new result is down here, right? It's not within that box. So we've tried hard at N3LO to optimize the three-body interactions. None of them is inside that box. So you need some physics that moves your saturation point in this direction. maybe this gives a hint. It uses inconsistent CIs in the free body forces, inconsistent different constant values for the CIs in the free body forces than there are in the two body interactions. Okay, so why is that interesting? So because this is a work by Johannes Simonis, charge radii and ground state energies for a whole bunch of finite nuclei, closed shell finite nuclei. And so, as you might have expected, well, for the same interactions, the Hebel interactions, including the magic interaction, so it's the trend is exactly as one might naively expect. A too high saturation density leads to too small charge radii, and then too low saturation density to too large radii. So here's the magic interaction, Hebel interaction. It pretty much nails it down. In saturation energy, unfortunately, the box is no longer here, so this one-to-one corresponds. It's not as clear, but anyway, so perhaps the idea, and this goes along the lines several years ago by Vitek and collaborators, so N2LO SAT. So if you have an interaction that closely reproduces the saturation point, might also do pretty well in medium to heavy mass nuclei, is the idea. Of course, if you include saturation properties or heavier nuclei, heavier than the two-body system, then you have less of an extrapolation, or even if you include infinite nuclei matter, it's strictly in this case an interpolation, but still over a wide range. So, okay, so this is going to be a problem, but anyway, yeah. So what about the saturation box, which is here missing? Well, I promise you it's in the paper. So this saturation box is what we constructed here and has been used in many papers to gauge the good saturation properties of nuclear interactions, and it's essentially given by 14 energy serum energy density function. Also, this the blue ones and the orange ones, and so this is just the box here. It would be here, and also what is missing is a line here, a classifier that separates the RMF models from the STREAM models. But anyway, so the point is that this is just 14 energy density functionals, and in particular this one, that's the upper right corner. So the box is if that point were to be ignored, that box would be shrink down by quite a bit. So one should be careful with benchmarking power interactions with the empirical saturation point, because just looking at the skirms of the RMS, where exactly is the nuclear saturation point, and what the key constraints to benchmark with. One of them, all of them. So this is not clear, at least not to me. And so, so there are, as you can see, all of those high confidence level confidence regions here from the DFT estimates, the DFT models, are at 95%. So not all of them can be accurate and precise at the same time, because they exclude each other at high confidence levels. Again, all of those regions are 95% credibility levels. So something needs to be understood here, but I also would like to emphasize that the saturation point is not an observable, right? So we computed here in this thermodynamic limit. The DFT models are calibrated to genuine nuclear observables and then extrapolated to infinite nuclear matter. So, but anyway, not all of them, not all of the DFT models can be at the same time precise and accurate. And so if you go to the paper, you will see a support vector machine with a hyperplane. We had a talk about this yesterday, that clearly separates with large margins. Wonderful, Pablo. There you go. Clearly separates the RMS from the skirms. So essentially, if this classifier were to be trusted, you give me an unlabeled saturation point, and this model tells you.
So Christian, which of those RMF models has been properly calibrated?
So all of them, right?
What is your definition of properly?
Excellent question.
I mean, posterior.
So we get posteriors for there, but it's in the small, in the thousand of percentage.
Oh, chi-square.
Guys proceed with their. Except for the green room. Right,
What is green one?
the one that
So,
we need to.
yes.
Arguments.
So here we go. So, the green one is by Pablo and collaborators, the Frontiers article. And, as Swapna said, all of those ellipses are from a covariance analysis. Okay, so typically the terms predict, the saturation points, higher than the RMF models. So, as you can see here, and there's a distinct, separation between the two model classes. Is this something new that we found? No, certainly not. It has a long history. So the inconsistency can have multiple reasons, one or multiple at the same time, including, so there are different functionals, relativistic versus non-relativistic, different parameter estimation protocols, and of course, the infinite matter extrapolation from finite nuclei all the way to infinite nuclear matter. We should also keep in mind that infinite nuclear matter, as I showed you, has no Coulombic contribution and has no surface effects. There is no surface in infinite nuclear matter, which the surface here may actually be one of the main drivers why there's a I mean, the surface does not contribute to infinite nuclear matter. It might be one of the main drivers of this distinct separation. So let me be brief here in terms of interest of time. So there has been significant progress in the rigorous uncertainty quantification of DFT models, as you can see here, from covariance analysis more recently to Gaussian process emulation for uncertainty quantification and reduced order modeling here. So in particular, I want to highlight the work by Pablo here with the reduced basis emulator, which we have discussed in various inclination yesterday and this morning in different physics contexts. So which one to use here now for our for benchmarking parallel DFT interactions? Well, my answer to that is why not use all of them instead of picking just one? So, and the idea here is that Pablo summarized in this cartoon picture is our model assumption is that all of these DFT models here, either with uncertainty quantification or just point estimates, are modeled as random draws from an underlying normal distribution. That's just the simplest assumption that we can make, and an underlying bivariate normal distribution. Okay, so far so good, but the parameters of that distribution, so the mean vector and the covariance matrix, are unknown. They need to be estimated from the data. So, and this is a mixture model. In this sense, they are not known. So they have their own randomness. They are random variable themselves. And so we want to infer them from the data. By data, I mean any subset of those constraints or any DFT constraint you want to mix in. Go to our website and please feel free to use the codes to update this analysis with your favorite DFT models. So we'll not go through all the details here, but it's pretty much a straightforward application of Bayes' theorem. We are interested in the posterior for the two model parameters, again, the mean vector and the covariance matrix. We choose a particular class of prior. We could use any one there is, and in fact, we have a full Monte Carlo implementation of this. But here we choose the normal inverse Wishart distribution, NIW. Why is that? Well, together with this likelihood function, so the standard likelihood function, and together with this likelihood function, the posterior, you can show analytically that the posterior is within the same class as the posterior, and that's called conjugacy. So you can do all of those calculations analytically, meaning extremely fast. And so the posterior is also a normal inverse Wishart distribution with the same parameters, obviously, but the values are updated. And it's a simple update formula that you just need to apply. So it's extremely fast because all the analytic calculations have been done beforehand. And then what we're interested in is we want to marginalize or compute the expected value of our model given the uncertainties that we have inferred. That's the posterior here, and that is called the posterior predictive. So that posterior predictive also has nice features because it's a student t distribution, bivariate student t distribution. which has a nice feature. It has heavy tails if the degree of freedom is small, and if the degree of freedom goes to infinity, it has that the limit is a normal distribution. So very simple calculations are over here, and it's extremely fast. And we applied this to again, the box is missing here anyway, so we applied this to the data points that I showed you, the 14 data points that are defines that commonly used saturation box. And here I'm showing you the prior predictive, which is completely data agnostic. But I'm showing you just as a reference the data here as well. So as you can see here, the red is the 99% credibility level, and 95 is here in blue. We treat this one as an outlier. Feel free to ask me later why that is. We had some very useful conversations with Alex Brown about this. Anyway, so this is our prior information that we plug into. So essentially in this layer here, and then we can apply this entire framework here. And as you can see, it learns the distribution function, in this case, binary T distribution, with here the marginal distribution functions that are univariate T distributions. You can show this analytically as well, and the 95 credibility levels. Keep in mind, this is useful to know, but the underlying saturation point is a correlated, although weakly correlated distribution function, a student T distribution in this particular case. So
What are the degrees of freedom when you're done here?
so in this case, it's at 17, so already large, but yeah, yes. But I will show you an example where this is no longer the case in a second. And so we found only a relatively mild. So this is a data limited application. We only have like 14 data points and data only 8. So it's pretty much data limited, especially from what we heard yesterday perspective. But we only found a mild prior dependence. And again, all the Jupyter notebooks are online. So, but there's one issue with this whole thing. So far, it has been quite simple, but this saturation point is typically not observed. Why is it not observed? Because here's a distribution function. We don't know exactly where the estimate for where the saturation point is. We only have a distribution that says within that uncertainty, the point might be somewhere in here. So what to do about it? And that was the key insight, I think, from the statistical point of view. This one is not observed. What to do about it? Well, you need to marginalize over this uncertainty, and so this parameter here, the saturation point itself, becomes a random variable. And so you can do this. You can just use the marginalized likelihood, but it breaks conjugacy. You can do this. Of course, there are very powerful MCMC frameworks out there. There's one Jupyter notebook online that does that, or with minimal effort could do it. But we thought, well, maybe there's something better we can do. And because we take all of the uncertainties here from the model developers like VTech and Pablo or Hawk at face value, we do not change it. We are not trying to reevaluate the underlying uncertainties. We just take them at face value. This marginalization and applying Bayes' theorem commutes. So what does this mean? That means that we can draw random samples in this saturation plane. So this is one set here. Again, the prior predictive and the posterior predictive. And I just picked from 8 of them. We categorize them in classes 1, 2, 3, and so on and so forth. 8 of them. So 8 data points, and we just draw, let's say from Pablo's distribution, 1 point. And so this is exactly here. So we draw 1 point, maybe this one. We draw 1 point, apply the conjugate prior approach, get a student T posterior predictive, and then repeat this process. And this is exactly, again, a mixture model that we are mixing multiple student T, or formally speaking, an infinite amount of student T posterior predictive distributions into one global posterior predictive. So what we do is here, this is just a simple, it's just ordinary Monte Carlo. There is no interdependency between, there are no change, there's no interdependency between different random samples. You just sample the space, you get a student t distribution for each sample, and then in the end, you just collect all of those posterior predictors that you get in many, many iterations, 10 to the 6, 10 to the 8, and you draw a correlation or corona plot like this. And what you get, this is exactly what you get, the marginal distribution for the density, the marginal distribution for the energy, and here's the resulting distribution function. The resulting distribution function is not necessarily student t, bivariate student t, but we found by just fitting a student t distribution to the results to the samples, it's actually pretty well described by that, as you can see here by the confidence ellipses or regions. And we think that maybe an analytic model for the saturation point makes it quite easier for the practitioner to just use it. And there are tools available on this in this GitHub repository. You can just use this plot routine to easily plot this or any of the student t distribution. So okay, coming back to I think Sebastian's question. So this is our new results. All of the interactions saturate within the 80% credibility level, which is here the green one. So I think it's an interesting question. What are the degrees of freedom to reproduce that point? If that point is to be reproduced, that would be I think an interesting question to discuss. But anyway, I think the key new aspect of this work is do not think, well, my suggestion is, my recommendation is saturation blocks should be taken with great care, because I mean, strictly it's a uniform distribution. Does it really mean an interaction saturates inside that box? It has good saturation properties and outside not. So I don't think so. And so this new result allows you to show the uncertainties in the underlying empirical saturation point from DFT by just plotting it at multiple confidence levels. And my suggestion would be using these ones. Real quick, okay, the results are not present anyway, so I'll skip that. So what we found is that the correlation, so for the symmetry energy, the results are in pretty good agreement with previous estimates of the symmetry and its slope parameter here. And the uncertainties are, the uncertainties come only from neutral matter calculations plus our constraint on the empirical saturation point, which is very, very tight. So the uncertainties in this plane are almost entirely given by pure neutral matter calculations of chiral effective field theory, which are more precise, more accurate than corresponding symmetric neutral matter calculations. And the uncertainties are remarkable, I mean, noticeable, as you can see, and but they agree with the also not visible PRX result at the 1.5 sigma 1.5 sigma confidence level. Okay, just to wrap up real quick. So we have proposed a Bayesian framework that infers the unobserved true empirical saturation point. Empirical, I mean from DFT, which allows you to benchmark your chiral interaction and many-body frameworks with that point. And you can plot it at multiple confidence regions as opposed to just a uniform distribution or whatever. And here are our numerical results for the saturation points and the symmetry energy and its slope parameter. But keep in mind, again, the marginal distribution at some confidence level does not give you access to the correlation structure of this non-observable in this particular case. So please keep that in mind. And there are plot routines where you can plot our posterior predictive distributions. Thank you very much.
A very nice talk, Sebastian.
Yeah, very nice. So you have 3 adjectives: unobserved, true, empirical.
Wonderful. Thank you for that question.
Can you maybe elaborate a little bit on that exact choice of word, because it sounds like very carefully picked.
Yes. So unobserved. So the I mean, this is statistical language here. So in this case, it's a point estimate, it's observed because the developer tells you that is the saturation point. If you believe that is a different story, but it's observed. In this case, it's not observed. You don't know where the true underlying saturation point is at.
So observed refers to the statistic, not the statement about observable nature of the.
Wonderful. I think we've added multiple footnotes in the paper, unobserved in the statistical meaning.
Okay,
And then true is the belief, the assumption that there is a true saturation point that, and all of them are random draws from that underlying distribution point, saturation point. If that exists, is a different story as being said, but under this assumption, that's what we get. Pablo.
I want to comment on that from a statistical point of view, you could, for the same quote unquote observation, we need a different word, that you have these points in there, you could say, I believe 100% that this person believes 100% that the saturation point should lie in here. A different view of this is to say, they didn't report uncertainties. I don't think they think that they are 100% sure that they should be here, but they just didn't do an analysis of you. So you could construct a modeling where you try to give some estimate of what should be the uncertainty quantification for this particular point. What we found is that since most of the thing that is driving the big uncertainties on the final estimate is the systematic difference between models rather than the intrinsic QQ of each one of them, it didn't matter as much for this particular. Just wanted to make that point.
Yeah, just to emphasize this, right? So this discrepancy determines the uncertainty. It's not this uncertainty, because again, this is at 95% credibility, right? Yeah. But it depends on how you want to phrase it. Either this model developer didn't do uncertainty quantification, which might be a little bit offensive, or they believe that is the true saturation.
why is it offensive? Either they did or they didn't.
Nobody can
I don't
say,
know.
I am 100% sure that this is the point that my model says. So
I haven't talked to all of those developers, unfortunately. So I think Kyle was first, if I'm not mistaken. Sorry, Vita.
So the assumption here in your error bar, in your distribution you get, is
Yeah.
that every one of these models comes from that distribution. It's a random sample.
Yes.
That eventually obtained.
I like where you're going with this.
Well, I'm not gonna go anywhere further than that. I'm just gonna leave that point.
Okay, so let me just add one sentence. Yes, they are collinearities between the models, so they are not independent.
Yeah.
And so I think this would be very nice in future work to understand. So in general, I would, from an EFT perspective, I would appreciate that the EFT is insights and perhaps future work in trying to understand the systematic discrepancy and perhaps minimizing.
Because Pablo's distribution, as you called it, there's 5 million dots that could lie within it.
Yes, in fact, I should have called it Pablo's and Kyle's, but anyway, so yes, thank you. I think Vitek was first.
So, Christian, so I understand what we are doing,
Yes, please.
but the box represents a no judgment zone. Okay?
What do you mean by no
take a
judgment?
Judgment on those models which you put inside your box,
Mhm.
here, right? And, some of those models manifestly violate, some observables. They are not able to reproduce, some physics, okay?
Right.
But you put it all, okay, into the box, and then you use statistical methods to derive the saturation point. So I'm just afraid that some people will consider your statistical estimate as a valid empirical point. But this, one has to realize that this dramatically depends on what you put in the box, right?
So,
This is what you say in the paper.
well, so I agree with that, but so you implicitly make the assumption that some of those models are to some extent invalid.
Yes.
Or have strong issues. So once again, and thank you for Pablo for pointing this out again. Let me be very explicit. The discrepancy here does not come from the uncertainties here or here in the skirms. It comes from adding RMF or vice versa, treating both models simultaneously. And it's quite the result is interestingly, let me put it this way, insensitive to what exactly you do here because of that very fact.
No,
So,
my point, Christian, is perhaps, suggestion for some work to do in the future.
oh, yes, I agree.
Is that perhaps, one should agree on the data set.
I agree.
okay, which would be used to calibrate those models.
Yes,
We agree on the data set. We take not just few masses and few radii. We take, some other observables which are important according to our current state of knowledge.
yes,
And then we calibrate those models. And this would be great because they have different functional form, different density dependence.
Right.
And then we arrive at some answer. But, underlying data set would be the same.
yes. I couldn't agree more with you, and so I hope that this talk and our paper addresses the point from an EFT perspective. You are the expert in DFT and more. On my perspective is EFT. So what should we use to benchmark our interactions? And I think more communication, at least speaking for myself here, would be fantastic, and coming up with new distribution functions to use for this kind of study. I think Jerome was first.
Thank you very much. Yeah, so I imagine that what Vitek suggests will help to clarify the situation, but I still believe that there will be a model dependence or systematical difference between relativistic models and the others.
Right.
And the reason might be because the average density in nuclei is not the saturation density. It is maybe 2/3. I mean, it depends on the nucleus. From one nucleus to another, the average density changes because of the surface.
Yes.
But it is about 2/3 of saturation density.
Yes.
So if you make a similar correlation plot, but where you change the density instead of being saturation density of each of these models, 2/3 of the saturation density, I imagine that you will reduce the systematic error bars.
That's an interesting point. Perhaps we can talk more about this. I'm very interested in that. So perhaps just to also reiterate this, so one might expect that those have too low charge radii, right, and too high charge radii, but they were fit to the same data or similar data, right? So the surface plays an important role, which does not contribute to our infinite matter.
Yeah, what I say is just that from 2/3 of saturation density to saturation density, you are doing an extrapolation,
right?
Which is based on the density dependence of your model, and therefore, and this is totally unknown. So, so this is what might bias this correlation factor.
I think Paul has a comment on this.
Well, I mean, my comment is that, well, the comment is that I think it's, and that's probably one of the handicaps of the current EFTs, is that you cannot go to very, very large nuclei with confidence, right? And I think, I think lead-208, it gives you very clean evidence that there is saturation. And of course, if you calibrate your functional to finite nuclei and then say, I'm going to predict the following equation of state, then of course it saturates, right? So I think that for the saturation purposes, I think we're looking at the correct density. But the question that I have that I hope someone can explain is, there have been a lot of rumbles about chiral EFT being able to actually calculate the properties of lead-208, right? So if you can do that, then of course, some of this discussion is irrelevant because you can really look at finite nucleus.
Yes.
And then compare to experiment. What is the status of that work that claims that we have computed with chiral interactions the properties of lead-208?
So I think it's unfortunate that Argauto is not here.
But what's your impression or the impression of other people here?
No.
Do we trust that? We trust the calculation of lead-208 doing from R&D?
I think that one should read this paper,
Yeah.
which I think it's really, breakthrough.
Yeah.
As a statement that we can solve 208 value problem.
Absolutely.
So this is not that we can reproduce the properties of lead-208. If you look at required precision of what we would like to understand by reproduction, it's not there. Look at energy. In the plot you will see energy per nucleon, and lead has 208 nucleons, and the error bar is tremendous. Okay? So we are not arrived at the level of precision, which would satisfy us, right?
Mm.
Same with skin. So I would not say that we reproduce properties of lead-208, but we arrive at lead-208.
Yes, I think that's a wonderful concluding remark. So certainly it's the first ab initio calculation of
I mean, I
just
think
three,
it's a
three of them.
breakthrough,
But there are many open questions that I have at least, so the interactions were pretty solved and so on and so forth. So, but yeah, we are getting,
So we
by
agree
we,
that
I mean them.
that it's a breakthrough, but as far as trying to inform saturation properties, we're not there yet.
Yes. I've given a talk where some of the main results were missing. I think this is a good strategy because that allows me to emphasize and hopefully increase your interest in reading that paper. So thank you very much again.
Okay, let's think. Yeah, let's see. So this computer has to load my, because my computer's been busy.
I'll be really good, so don't worry about the all DFT and all those. No, the problem. None of those.
Payments download. It's a weird location.
Let's do it to. Let's go to desktop.
Yes.
Again, so it was a long project.
Let me do this first.
Because it was solved by most valuable friend, you know, in the 80s. Electric games. I mean, child density. Now we do have proper. Okay. That depends on the radius.
All right, so our next speaker is Nuwan Yapa from Florida State University, and he'll talk about emulators for unbound nuclei.
Thanks. Hello, everyone. So this is going to be my talk. We actually started this a while ago, and I think Streamline collaboration gives us an opportunity to take it all the way to the finish line. So let me start with a quick introduction of resonances and what the word means. You probably know that some nuclei that we can generate in the lab, they're only short-lived, and they are not bound. So oxygen 28 and 27 and 28, there are some examples that have been making the headlines recently. And there are also nuclei that have bound states, but they have excited states that are not bound. But studying them are important because they can appear in reaction channels of other kind of reactions and then contribute to their rates. So for example, I'm showing here this diagram from this paper showing the spectrum of beryllium 11. So in addition to the 3 bound states, there's an unbound state around 1.8 mark. And so the word resonance comes from the fact that these appear as resonances or kind of sharp peaks when you measure the cross section, both experimentally and theoretically, around exactly that 1.28 mark that we expect it to be. So now, just in pure mathematical terms, you can expect these kind of peaks to arise from singularities in the complex P-plane for the T matrix, because T matrix is proportional to the scattering amplitude. So if you look at a typical structure of the T matrix, this is what you'll find. So on the positive imaginary line, that's where the bound states live. On the real positive part is the scattering continuum. And just below that, on the 4th quadrant, is where you find the resonances with negative imaginary parts and positive real part. So in fact, you can actually use these points as quasi-stationary states themselves. So they will solve the time-independent Schrodinger equation for those corresponding complex energy values, and we call them gamma sets. And the imaginary part will be given like this, and the gamma value will correspond to the width of the resonance as well as the decay time of the short-lived state. And so the thing is, you can expect these gamma states not to be square integrable just because it has a negative imaginary part. So if you look at the wave function, it's not going to be bound, and in fact, it's going to be blowing up exponentially in the asymptotic region. So this is a problem. One way to solve this problem is use this thing called complex scaling, which is where you just take the coordinate, either radial or momentum, and then multiply it by a complex factor given some condition. And after you do that, the wave function will actually the exponential blow up will be suppressed, shown by this yellow curve. So there's another way to look at this method, which is first consider the complex P-plane. We can expect the top half, any poles in the top half plane to have a bound to be bound basically. So that's where you can those states will be admissible in the Hilbert space. And what complex scaling does can be thought of as a trade-off, where you trade a section of the Hilbert space with a section of what we call but the name for that is the Hilbert space. So it is this trade-off allows us to calculate these poles, the gamma states that I mentioned. And so this is not the only way people have been using to calculate resonances. There's a whole forest of techniques. The other one we're interested in is called the Bergeron basis, and then there's also a method called avoided processing that we have been playing with. And so there are different ways to implement these techniques, of course, depending on how you want to construct your free-body basis. You can either implement in a finite volume basis, or you can use a Norco shell model, and this popular Faddeev-Jakubowski formalism is also another way. So in this project, we have studied using complex scaling in finite volume, also complex scaling in the Norco shell model, and also our final goal is to implement this gamma shell model, which is a combination of Bergeron basis and the Norco shell model. Excuse me. Yeah, that's our project, and that's what I'm going to talk about. So to our first point, this is what a finite volume calculation with complex scaling looks like. So basically, finite volume means you have a finite box with periodic boundary conditions, and you put your particles in there. So it's going to be an ab initio calculation, and because of the finite volume, you can expect some finite volume effects, which means the energy will have some dependence on the size of the box. And so this is a gamma state, so it has imaginary part, so I'm showing both here. But the good news is that we have a formula to predict this behavior, predict the energy shift as a function of L. If you know anything about the Lucia formalism, this should ring some bells. So the technique, so the idea here is we can calculate the system for different values of L, and then fit those points for this curve, and then get the L goes to infinity limit, which is where the physics is obviously. So that gives so this is kind of easier said than done, because even those points calculations can be really expensive. So that gives us a great way to utilize these reduced basis method / machine learning techniques. So the game plan goes like something like this. You take your Hamiltonian and exactly solve it for different L values like this, and then we use that as a training basis to build an emulator and generate even more points. And then you can use those many points to fit your Lucia equation and extract the L goes to infinity limit. And this technique is, so we gave it a name, we call it FVEC. This is a very straightforward extension of the eigenvalue continuation, sorry, eigenvector continuation method that you are all familiar with. That's not the only way we can employ reduced basis methods. The other way is that the more vanilla implementation of the eigenvector continuation, we actually change the Hamiltonian, some parameter in the Hamiltonian, because for example, the coupling constant or the strength of the potential, if you change that, you can expect the resonance to move around in the complex plane. And if you make it strong enough, it can even become a resonance. So what we can do is we can either consider training for very narrow resonances. So that is closer to the scattering continuum, because numerically those states are very easy to handle. And then use that to extrapolate the broad resonances. Or you can actually think about building the emulator only from bound state information. So which is going to be more useful because bound states are very trivial to solve. So just to illustrate, I have toy model with two particles, and this is we're training on this blue arc and trying to extrapolate these broad resonances. And we also took the liberty of calculating some uncertainty quantifications, and it looks like it works very, very trivially. So there's only one detail you have to think about, which is because of the complex scaling, the Hamiltonian becomes non-Hermitian. So there's something called C product that we have to be aware of. Other than that, it's pretty straightforward. Just to make sure that this works in the three-body regime or any few-body extension, we have also considered three spinless boson system, again of toy potential, and we have considered the Norco shell model with complex scaling. So this Norco shell model with complex scaling can be also understood as allowing the quanta of your harmonic oscillator basis energy quanta to be complex, to take complex values with some scaling complex scaling factor. So here, if you look at the results, I think you can appreciate how even training with these very narrow resonances, which are almost completely real, but that emulator is more than enough to extrapolate all the way deep into the complex plane. Yeah, so that's very good. And like I said, we can also think about using bound states only to extrapolate resonances, and that's what we have done in this work. This is a little tricky. In fact, it won't work naively if you implement eigenvector continuation. So we had to do some funny business where you augment the EC basis with some artificially manufactured vectors. So without it going into too much details, I'll tell you what we do is we just consider the wave function as two parts with interior region and the asymptotic region, and do a very trivial thing to make it compatible with resonance, the asymptotic properties of resonances or the gamma states. So again, to make sure this works in the free body regime, we do a calculation in finite volume with complex scaling. Again, we had to do this CAEC trick to make it work. And for three spinless boson for these toy potentials, this is what we see. But training at this very close to threshold bound states, but we extrapolate these resonances pretty easy. Now, like I said, this is the.
Can I ask a question? For your potential, is this all finite range, very short range function?
Because these are Gaussians, I think we can call them finite range here.
Yeah, when is it shifted? Like it goes out to 3.3 or 4 units.
So what motivates that design?
Getting a resonance also in the two bodies. So this potential produces 2-body and 3-body resonance, and that 3-body resonance, it doesn't have the 2-body decay channel. It's a genuine 3-body thing. So only decay to 3-body.
I think his question is more like why we chose this potential. Is that it?
Yeah, so that potential achieves that is from some other work that we came up with it.
Cool. So yeah, like I said, we also this is some main focus currently, which is to implement the Berggrund basis and do some similar extrapolation. So I can give you a quick introduction to Berggrund basis like this. So think about the completeness relation, where you normally have to expand in your eigenbasis, which would contain bound states as well as the scattering continuum. So don't worry about this for now. So you will have some and an integral. Now, if you just take this integration and push the contour below these resonance poles, you can expect so these resonances poles are simple poles. So you can expect from the residual theorem to to make it so that now we have to include these poles in our completeness relation because they are simple poles. So this would be the basis in the Berggren technique. And now when we have using this basis, we can construct the Slater determinants that lets you construct a free-body Hamiltonian. So we don't have any calculations so far, but I can give you a quick demonstration. So this is again a toy potential, but this is a very simple Berggren basis implementation without any faults here. That's just a deformed contour basically. But so I think you can see how. So if you know about this technique, you will know that we cannot actually expect to be able to compute anything below this contour. But using eigenvector continuation, it seems to even work below the contour. So you can even claim that EC basis outperforms your original basis. So which is a very bold claim, but in hindsight, you can actually consider the math and see that it's not very surprising. Sorry, yeah, go ahead.
So if you can't normally use the Berggren basis to compute things below the contour.
Yeah.
How do you know that what you've computed below the contour has meaning?
Yeah, well, I have used another technique to benchmark these points. Actually, they are shown by these yellow dots, which are hidden inside the green ones.
What is this other technique?
I think it was just a complex scaling with a large enough angle so that we can get these resonances. So yeah,
You can also announce the Berggren basis. Sure.
I noticed that now the trainings are actually also the reference state.
Yeah.
What was the situation that we actually have just trainings on the bounds?
That's a good question. That's currently being studied. I can tell you it works, but we don't have a very good mathematical justification for it. So that's why I didn't claim anything in this talk.
Yes, actually, in my talk, I will show similar things like all these emulators actually outperform in a way to say that it actually outperform the original method. They actually can extrapolate to see the references.
Yeah.
Even the original basis couldn't see it.
Exactly. Yeah. Yep, that's right. And so that concludes my first part of the talk, but unfortunately I have a few more slides here to sit through. So this is a completely different project that I'm just a newcomer to. All of our team could be here today, so I was asked to present only a couple of slides on this. So this is an emulator for calibrating covariant energy density functional. Maybe I can take some questions from the demo. Okay, so why do we need relativistic covariant energy density functionals? Because neutron-rich matter is notoriously non-relativistic, so we cannot get away with the Schrodinger equation anymore. You have to solve with the Dirac equation for the nucleons, so Klein Gordon for the mesons, and Poisson for the photon. So you can also call it relativistic mean field theory. It's same as covariant DFTs. This has several applications like we just heard from Christian's talk. Can do Bayesian refinement and calculate equations of states for neutron stars. And with this data, you can do real cool predictions, like from this work where they have predicted the equation of state as well as the relationship between radius and mass for neutron stars, which seems to work really well. So we usually start with a theory like this, with some mesons, and so this is the nucleon field, and this term will encompass that I will not show in explicitly all the self interactions between the mesons. They are important, but it's too long to show here. So the classic problem that we run into in this kind of calculations is that the Dirac equation will have source terms, which are the scalar potentials and the vector potentials and other kind of tensor potentials, if you want, that are created by the meson fields. So to know the meson fields, you have to solve these Klein Gordon equations, and they have source terms arising from the neutron and the proton densities. It's like a vicious cycle. So usually you would use an iteration technique to solve this, but I think it's completely impossible to solve as a simultaneous set of equations. But using our reduced basis methods, we can actually do that. And you would use this Galerkin projection technique to construct a set of reduced basis equations that you can solve simultaneously. And get some cool results. And secondly, we also interested in this particular project where we use the empirical interpolation method to accelerate the online stage of the extrapolation even further. Do you have any comments? No.
No.
Okay, cool. So yeah, so this is not a very good representation of the technique. I just chose to show this. So usually the source potentials are not linear in the coupling constant, but you can kind of approximately linearize them, expanding in such a way that you would absorb the non-linearity into these functions as functions of coupling constants. So the problem is now how to learn this function. So that's another project that we're interested in. Yeah, that's pretty much it. Thank you.
Everyone, very nice talk. Are there questions from either part? Yeah, Josh.
So, great talk, a lot of very interesting, continuum emulation stuff. For the, training on the bound states to go into the resonances, you said there was a technique that you used to basically inform it on, I would assume if you didn't do anything to inform it, it would just continue along the axis and not deviate at all. So what did you do to force the deviation or tell it that it can like explore?
That's a great comment, and exactly like you said, you can show mathematically that you shouldn't be able to predict complex poles if you just have bound states, but we do. It's a very simple technique where we just take the training vectors and then you take the complex conjugate, or equivalently you separate the imaginary and real parts of the vector. And so that your basis is going to have double the size. See, but as to why it works, it's a little involved. I didn't get. I need some diagrams to explain, but I don't have it here. So, but yeah.
Maybe if I can help, one way you can understand this is if you take just bound state with real wave function, you're never going to get any imaginary part.
Right. Yeah.
But what he does is he expands the bound state in, for example, the Bergen basis or complex scaling basis, that you have an imaginary part.
Oh, with the rotation, for example.
Yes, and then once you have this imaginary part, it does an extra rotation, to say, so that you get to something that is outgoing of these bound states.
Okay, so you basically change your boundary conditions from a bound problem to
you don't change the boundary condition.
or your rotation.
You make sure that your basis contains enough, not you are doing something that you can extrapolate resonances from bound to bound state.
Right, so you're forcing it to have an asymptotic
In some ways.
Yeah, but the bound state calculations, themselves. I mean, for this work, we used a rotated basis, but you don't have to necessarily. You can transform it after the fact. Yes.
Oh,
Yeah, so excuse my ignorance, but can this technique used to say compute scattering between say helium-4 and the neutron? Like we put them in a box and then complexify the coordinates and then compute the binding energy of this five-body system as a function of the box size, or but how can I tell whether it's exactly neutron helium-4 or like something else? I'm just ignorant, okay, so.
So are you asking if one of the particles are spectral particles or?
Well, I'm saying, I'm gonna identify a specific, if I have a helium-4, if I just put 5 nucleons in a box.
Yes.
Let's say 3 neutrons and 2 protons, and then I complexify their coordinates, that's what I understand. And I'm going to compute the binding energy, the ground state energy of this system as a function of L.
Yes.
And as a function of how much I complexify, I think.
Yes.
Will I be able to extract the neutron helium-4 phase shifts?
I don't think so, because these both bound states and resonances are poles of the S matrix, whereas the scattering states are. They're on the branch.
If I may, you don't even need to do complex scaling if you just want scattering phase shifts. you would need to take into account there's like, because both the bound states will have an exponential volume dependence, and then the Drischler scattering formula would have some power law volume dependence. In principle, you can. I don't think anyone actually derived the 5-body Drischler quantization condition properly, but you can probably get away with doing the 2-body and doing some topological correction from.
Yeah, because I don't want to, I don't want to stop with that helium-4 and, in principle, I could do that, but in principle, I would like just to look at properties of this 5-body system.
Yeah, but if you do the complex scaling, I would say you would see helium-5 as a resonance as a complex energy. There's only some complex energy plane, and you would find if you do complex scaling in each relevant coordinate, we did this for the 3-body system and showed that it works. There's no reason to believe it would work more. You would find that complex energy if you diagonalize your complex energy.
Well, you need to diagonalize it. You don't.
Yeah.
You can't just get the ground states for different L.
Well, you do line shots at each volume, right? You have like some sparse representation of your bases in the box, and you do line shots. And then if it's complex, you have to, get to that complex value within the spectrum. That's the tricky part where actually EC can help you again, because you can make it bound and then use what Nuwan showed. But in principle, yes, you can.
Yeah, maybe ask question that correct me if I'm wrong. So, first of all, you can, so if you have 5-body Drischler form, right, you can have 5-body system in a box and figure out the continuous scattering phase shift. Or if you apply complex scaling method, in principle, the solution is actually quantified, it's indivisible, right? So then you actually don't need a box. You just need some kind of basis calculation, because solution is not finite spatial localized. You can use whatever coverage of the basis to calculate system, and complex scaling method, people does use that to calculate the continuum flow, like a response function, like scaling and usually they can do it. So there's a Japanese group.
Yeah, you can definitely get resonance splitting methods, but in the box, I would say you can get it, and since it's a helium-4 plus neutron, it's like effectively 2-body. I would suspect we can generalize those 2-body cluster results for example, and diagram to specify that. So we haven't tried, but I would be optimistic.
Thanks. Okay, are there other questions? Not
Just want to add one comment. I started getting into this business in the last 2 years, and sometimes I find it very confusing when people talk about that like the classification of poles on the complex plane. Okay, so that's the intuition you get from 2-body system.
Yeah.
As soon as you get beyond 2-body system, it's even hard to define momentum for one momentum variable. So the fundamental property is actually energy, the many-body energy. That's well defined. Just a comment. Because I see so many thoughts in this kind of talks.
Yeah.
Like people talk about momentum plane and resonance, bounce, and all those things. That's well defined for 2-body problem.
Yes.
But if you go to a 8-body problem, there's no defined definition.
All right, with that, let's thank Nuwan again. And we'll take a coffee break until 10:30, and Pablo has an announcement.
Important things, friends, for lunch today, on Fridays, we usually have lunch with a lot of people from the lab in the atrium. And we bring Mediterranean food that is vegetarian and non-vegetarian options. I need a show of hands. I'm going to bring it here. How many wants to have lunch in there so that I can order extra food? Instead of walking to the thing, okay? So as soon as we get out, I will leave earlier, so. Okay, like 12, 30 minutes. Everybody else is going to, Vic, will I count you?
Yeah.
Okay. You don't have to, it's not an obligation. It's only if you want, it's nice, we all sit together, okay, perfect. I have an estimator. With money, yeah. Yeah, take the perfect.
Okay, yeah, if you.
I have it.
Yeah. What you can do is you can project by Zoom and then it will go that way.
Hey, good to see you. Very nice to meet you. You'll see that. Pretty good. Yes. Sorry. I changed my website the other day. Now the director. Yeah. French.
try to use board. I wanted to make some plot last night, but I didn't.
So what she's doing is, I have by, right on the 56, and I know that I am from
I think the concept the French government has by the United States concept some growth. They also have this essential. Yes.
Running back then. If you go to the program. Yeah, just check. I think it's also the French government.
Here they were very responsive and very positive. Helped me a lot. So very good.
So you're now in Morton's home office?
Yes, yeah. So you know.
Oh, yeah.
So. So what
Better if you
about,
did that.
yeah, so this afternoon I have a problem.
Okay.
So I have a meeting at 2:00 and but I didn't put the head. That'd be nice.
So I went and looked into it after we were talking yesterday about the other condition and what the condition for emitting a fixed point, at least in the 2-point coupling that I saw, was that it is at input equals 0, the derivative needs to be non-zero, is the other condition. So
Okay, it needs to be 0, but the derivative needs to be non-zero. Okay, so if it just passes through and has a kink, then that's.
And they also said that for results where you have an activation function where it's non-zero for an input of 0, you can apply an appropriate constant shift.
Okay.
And it will make it so that you can have a fixed point.
I assume the slope needs to be positive too.
Yes.
Yeah, but it's okay. It's like the really with the kink there on one side, it's enough.
Yes.
Okay. Okay.
Yeah. So that was, I basically, it was bugging me that I couldn't remember it, so I looked it up. But yeah, that is the situation, as long as you have some non-zero derivative.
Yeah, that's familiar with when we think of fixed points from like RG flows. We want to think of the behavior where there's a slope, because then it's sort of, it's an attractive.
Yeah. And yeah, because I'm trying to remember how they formulate it. They basically do it in terms of these like susceptibilities that you need to have equal to 1 if they're greater than or less than 1, then that leads the driving behavior to infinity. But yeah, those conditions then when you go to apply doing the recursion should end up even to. I just wanted to let you know because I was thinking about that last night after.
Yeah.
Just a 5-hour drive. So that's not here, right? So I'm not sure well, I was her biking to all the places here, and it was almost impossible.
Yeah, I know. I
especially in the winter there, because the leaves are older than